Assalamu alaikum everyone. My name is Muhammad Ubaid Khan and today we are going to start our chapter 0 of the book The AVR Microcontroller and Embedded Systems using Assembly and C language. This is the second edition of the book and we have our chapter 0 which is Introduction to Computing. So let's start. These are the topics we are going to discuss today. These include internal organization of computers, the different parts of a computer, which include input-output devices, memory, and CPU. Uh, we will see how these parts are connected. Obviously, they are connected on the motherboard. We connect memory to CPU, we connect our input-output devices to CPU, and we are also going to see how computers work. So here we have our internal organization of computers. We have our CPU, which is the processor, of course. It is the main mind of the computer. We have our memory, which we have memory of two types. It is primary memory and secondary memory. We have our input-output devices. Our input devices include our keyboards, mouse, sensors, etc. And our output devices include LCDs, printers, and hands of a robot. There are a lot of input and output devices in the world. You can look it up if you want. Then we have our memory. It is everything that can store, retain, and recall information, such that hard disk, a piece of paper, etc. And when we are talking about computers, the memory in computer is of course storing data in digital form, and we can recall the information whenever we want. Uh, and as I told you guys before, we have two types of memory, primary memory and secondary memory. So when we talk about primary memory, which is our RAM, it is a volatile memory, so it is erased whenever we turn the power off. But of course a hard disk or an SSD can retain that memory when power is of course not on. So then we have our memory characteristics. This is the capacity of the memory. These are the number of bits that a memory can store. We have 128 kilobits, 256 megabits. Uh, these differ, of course. Then we have organization of memory, how the locations are organized. For example, 128 by 4 memory has 128 locations, 4 bit each. So it has 128 locations which stores 4 bit in each of the blocks of the memory. Then we have access time. It is how long it takes to get data from that memory. So when of course our processor gives the command to retrieve that memory, it is the time it takes to get that memory. Then we have different types of memory. We have semiconductors, we have non-semiconductors. Our semiconductors type include our RAM, etc., and our non-semiconductor types include our floppy disks, etc. So the semiconductor memories include ROM. We have different types of ROM as well, which include mask ROM, PROM, programmable ROM. We can program this ROM, but we can't program the normal ROM. The manufacturers program it, and then you cannot change it. Then we have EPROM, EPROM. We can also call it that. It is erasable PROM, so it is programmable, but it is also erasable as well, so a user can erase it, but this ROM is difficult to erase. It has a lot of steps into it. But when we talk about the double EPROM, it is electronic erasable PROM. A simple user can just simply erase it from the BIOS of the computer and reprogram it whenever they want. Then we have flash EPROM. It does the same thing as double EPROM. So then we have our RAM. We have basically three types of RAM: SRAM, static RAM, DRAM, dynamic RAM, and non-volatile NVRAM. So normally the RAMs are volatile type, basically, which means that the information that they store is erased when the power is turned off. But there's also a non-volatile type as well, which retains the information whenever power is off as well. Uh, so let's move on. So here we have the memory ROM, mask ROM type. programmed by the IC manufacturer. As I told you before, this type cannot be erased by us by a user. It is the code is burned into it, and a normal person cannot change it. Then we have PROM, one-time programmable. You can program it only once. So once it is programmed, you cannot change it. Um, this is EPROM. As I told you, it is erasable, but it takes a long time to be erased, and of course there are chances of failure as well. So it is not suggested that a normal person should erase it. It uses ultraviolet radiation to erase it. Erasing takes up to 20 minutes, and the entire contents of RAM are erased, and then it is reprogrammed as well. Then we have our double EPROM. This can be erased electrically, and it can be erased instantly, and each byte can be erased separately, and it is easy to program again as well. There are a lot of tutorials available on the internet on how to reprogram a ROM. Then we have our flash ROM. It can be erased in a flash, and the entire device is erased at once. And as I said before, it is also reprogrammable easily as well. So these were our ROMs. Now we talk about RAM. So this is static RAM. It is made up of flip-flops, transistors. These are very small transistors, and it is very fast because of course it does not have any moving parts. So it is static and it is faster. It doesn't raise its temperature very much, and you do not need to refresh this RAM. This is a big problem with other types of RAMs, that it needs to refresh itself to keep working. We have some disadvantages as well. It is it has high power consumption, and it is expensive, of course, because it does not have any moving parts in it. The DRAM, it is made up of capacitors. Yeah, it has less power consumption, which is an advantage. It is cheaper and it has high capacity. So the disadvantages of DRAM include slow speed, and it needs to be refreshed after a little while, because the capacitor is charged and discharged. So it needs to be refreshed, otherwise it's not going to work and it's going to overheat. So we move on to the non-volatile RAM. Now this is made up of SRAM and batteries and control circuitry. It is very fast. It can include infinite programs and erase cycles. It is non-volatile, but it is very expensive because of course it includes a lot of static parts. So yeah. So then we have the tasks that our CPU performs. So the tasks include, it should execute instructions. It should recall the instructions one after another and execute them. So our CPU should do these tasks. So this is how we connect our memory to our CPU. Here we have a schematic. We can see this part. It has the data lines highlighted. It has the data lines from D0 to D7, and then we have our address lines from A0 to AN-1, and then we have our read and write cycles, and our chip select, our ground, and our VCC. So when this memory is connected with our CPU, first we give our address, then we tell the computer which process we want to do, and then we send data or retrieve the data. This is the timing diagram of writing to memory. We apply our address, and then we give the chip select command, and then we of course give our command of writing or reading data, and then the data is simply written to memory. This is our reading diagram. We give our address, chip select, and then we tell the computer what we want to do. So here we want to read the data from memory, so we give the read data command, and then we read the data from the memory. Now let's see how we can connect our input and output devices to our CPU. There are a lot of pins on the CPU on the processor, and we can connect it we can connect all the inputs and outputs to our CPU. But of course we cannot just simply go and connect the pins to our input output devices. It has to be placed on the motherboard, and then there are ports which are connected to our CPU, and that's how they are connected. So this is a simple animation. CPU should have lots of pins, and it does have a lot of pins. So here we have our connecting input and output to CPU using buses. So like I said, CPU is placed on our motherboard, and then through the ports which are and then the ports connect our input output devices to our processor. So here we can see that we have our address bus, our data bus, and our control bus, which gives the read and write command, and our memory is connected here as well. And then we have n number of input output devices connected, through which we give the read write commands. So here we can see we have connected our input outputs and memory to CPU using bus, and in here we will see the operations of our CPU and how it retrieves data from memory, and how these input output devices work simultaneously with it. So how can we manage it? So here we can see that we have our input output and our memory as well. So our CPU will simply select where to get the data from using this input output and memory control bus. So the logic circuit enables CS, which is chip select, when address is between 0 and 15. So when our address will be between 0 and 15, the logic circuit will enable the CS, and it will retrieve data from the memory. And when it won't be, when it will be from address will be from 16 to up to whatever the number is, it will go on and choose the input output devices. So how could we make the logic circuit? So we have our solutions here. Write the address range in binary. We can write the address range in binary to tell the computer how it should switch between the two. So here we can see that from address 0 to address 15 in binary, and separate the fixed part of address. So this is the fixed part of address. The first four zeros, we can just separate these parts, and using a NAND logic we can simply design this circuit whose outputs activates when the fixed address is given to it. So when we will give the fixed address to the NAND gate, it will uh, choose or enable the chip select. Here we have a few conversions which are necessary for us to understand the working of computer. Here we have decimal to binary conversion. We can do the process which is called repetitive division. We just divide the decimal number by 2, and then we store the remainder from most significant bit to least significant bit. So here we can see that 25 into binary is 11001. So now we have our binary to decimal conversion. In example 0-2, we can see that we are converting this number 11001 back into decimal. We have our weights. These weights are simply the largest power of 2 that we can fit here on the number, which is 16 here obviously. And then we have our digits. We just simply multiply these digits by the weights, and we just add those to get our decimal number, which is 25 here. We can also use the concept of weight to convert 39 to binary as well. So we write our weights here. Of course we do not know how many weights we should write, so we just simply look at the number that we are given. so it is 39. So we went to the closest to 39, which is 32 here. We just subtract that 39 from 32. It fits, of course. We get 7. So we write digit 1 here. Now we have 7. 16 cannot be subtracted from 7. We write digit 0. 8 cannot be subtracted from 7. We write 0 here as well. 4 can be subtracted from 7. We get 3. Of course, we then write digit 1. 2 can be subtracted from 3. We write digit 1. And then 1 can be subtracted from 1. We get 0. So we simply write 1 here, and then we add it up to get our 39. So 100111 is our binary for 39. Then we have our hexadecimal system. Here we can represent these hexadecimals into here we can represent these binary digits into hexadecimal. We just group 4 digits of these binary numbers. If let's say we and we always start from the right side of the hexadecimal and make pairs from the right side. If we have less digits on the left side, we just add zeros as we need, and then we can see that 0101 is 5, 11111 is F, and then 1001 is 9. So 9F5 is our hexadecimal here. We have this base 16 number system chart here, which has all the conversions, and then we can convert back from hexadecimal to binary as well by just simply writing the 4-digit binary of these numbers, and then we write it together to get our answer in binary. Then we have our decimal to hexadecimal conversion. So here it says convert 45 to hexadecimal. So what we are going to do is we will again use the concept of weights. We will simply get the closest number to 45, which is 32 here, which is the largest power of 2 we can get in this range. We will simply subtract it and then see which fits. So 16 does not fit here, 2 does not fit here, the other one do, and then we add it together to get 45, and then we just simply make pairs of 4 in here. So we can see that we did not have the last 2 zeros in here. They were missing. We simply added them ourselves, and then we got 2D, which is hexadecimal. We can simply we can do this again with 629 to hexadecimal as well. We will simply see which power of 2 fits into 629, which is 512, and then we can just simply see which fits and then add it together to get our answer 629, and we know confirm that this is our uh, uh, binary conversion, and then we make pairs of 4 to get our hexadecimal answer. We can do the same with 1714. We just simply see which is the highest power that fits here, and then we subtract it, and then we see what answer we get, and then we subtract, and then we subtract, and then we add them together to see if our binary conversion is correct or not, and then we can just simply make pairs of 4 and convert it into hexadecimal. Now this is hexadecimal to decimal conversion. So this is very simple. We can just simply get our binary conversion from our hexadecimal and simply write weights on it, and just multiply it together and then add them together to get our answer. So we can see it is done here. Then we have addition of binary numbers, which is very simple. We just follow this table here. We have a plus b, and when both are 0, we get sum 0 carry 0. When a is 0, b is 1, we get sum 1 carry 0. When a is 1, b is 0, we get sum 1 carry 0, and when both are 1, we get carry 1 sum 0. So we can just apply those here. So when we add these ones here, we get a carry here, and then that one carry is added with the zeros. We get 1 1 and then 0, and this is the carry 0. This is overflow um, here. Then of course we can also do this kind of conversion and check if it is correct in decimal as well. We use two complements as well to do all these operations as well. Here we have our 2's complement of 100 11101. we take 2's complement of it. What is 2 complement? We flip each bit and then we add 1 at the end. So what we will do is we will flip each bit and then we will add 1. So this is the binary number. Then we take 1's complement of it, which is flipping each bit, and then we add 1 to it and we get our 2's complement. It is very simple, and 2's complement is used for computers. Computers understand 2's complement and they work in 2's complement. This is our ASCII code, American Standard Code for Information Interchange. So this is the table of ASCII. This is very important in computing. Um, when we want to convert our binary into ASCII, we use this table to relay information. And these are some of the control characters of our ASCII. Null is null, SOH is start of heading, STX is start of text, and we can just use all these control characters in our programming. Then we have an example of address decoder. We have to design an address decoder for address of 300H to 3FFH. So let's see the solution. First of all, we will write the address range in binary. Here is our address range, and of course our first 4 digits we can see are fixed. So this will be our fixed part of the address, which we will have to separate from here. And then we will of course use our NAND gate to decode it. So this is an easy way to design it, and let's see a simple animation of how it is going to work. We see that address was applied first and then the data was applied, which was the fixed part, and then it just simply decodes it. Let's move on to inside of the CPU. Inside a CPU we have our program counter, which counts how many operations are done. We have our instruction decoder, which decodes the instructions that are given to our CPU. So now we see how our computers work. Here we have our memory, our CPU, and input-output devices, which are connected together by address bus, data bus, and our control bus. In our CPU, we of course have our ALU, arithmetic logic unit, our program counter, our registers, and our instruction decoder. So here, how this is going to work is first of all we give our computer the address. So here we are going to give the address 0. On address 0 we can see that it has the instruction 31. So that instruction is going to go to our CPU into the instruction decoder. So what is going to happen? The instruction decoder is going to decode this, and we can see that here the instruction says that whatever is in this input output device number 17, store that data into the register A. So we are going to see that after our computer decodes this instruction, the address is going to be connected to this input output device number 17, and let's say we have 9 on this device. So what it's going to do is it's going to perform the write operation, and this 9 is going to move from data bus and is going to be stored in A. After saving, our program counter will move to 1. So what it's going to do is then it's going to move on and give address 1 here. We can see that address 1 has C4 here. So our the C4 is going, the instruction C4 is going to move from our memory to towards our CPU through the data bus, and of course then our CPU is going to decode this instruction and see what it says. We can see that it says whatever is placed in the register B, the register A, we have to move that data into register B. So here it's simply going to move the data from register A to register B here, and it makes a copy of the register data which was stored in A. And as we can see as well that our program counter moved to 2. So now we will see that our computer will give the address of 2, and we can see that on address 2 we have 26 instruction. So this instruction is going to go towards our CPU. Our CPU is going to decode this instruction, and we can see that it says take data from. Now our program counter moves on to 2, and it gives that 2 into the address bus and uh, gets the second command. Here we can see that the instruction on 2 is 26. So this instruction is going to go to our CPU, which is going to decode it. And here we can see that the 26 uh, um, means that our CPU is going to give the address 6. On address 6 we have 5. So what it's going to do is it's going to move the 5 from the data bus, and it is going to store it at A right here. Now our program counter moves on to 3, and it gives 3 to our address bus. And in our address bus the 3 is going to go towards the memory is going to see and then give the instruction on our third address, and it has 81 on here. So 81 is going to move to our CPU. It is going to decode the 81, and what 81 says is move this 5 towards our ALU, move this 9 towards our ALU, and add them together. So our ALU performed the addition and stored that value into A. So now our program counter has also moved up, and now it's going to give 4 on the address bus, and we are going to see the fourth instruction. And the fourth instruction is EA. Our CPU is going to decode this instruction, and it is going to perform whatever it says here. So it has given 7 on the address bus and it is empty. So simply it is going to write here towards memory EH. So let's move on. Here we can see how our instruction decoder works. In here we have our opcode and our operand, and simply what our computer does is it uses opcode and operands together to perform or to decode our instructions which are given to our computer. These are the instructions in human language that we can understand. We can also understand this hexadecimal instructions as well, but it is hard for humans to understand this binary which our computers easily understand, and it just simply converts these hexadecimal instructions into this binary form, and our computer simply understands what it has to do. Then we have architecture types here, von Neumann versus Harvard architecture. The Harvard architecture is much better in a lot of applications as it separates both the data memory and the code memory, um and they both can just travel simultaneously or parallel together and perform tasks much better and much faster here, of course due to parallel processing. In von Neumann architecture we have both the code memory and data memory connected to the same data bus, address bus, and control bus. So only one of the data can move through these buses at one time. So of course we don't have parallel processing here, so that is why this model is kind of slow, but it is used as well in a lot of applications where we don't have to use parallel processing. uh, so here we have general purpose microprocessors and microcontrollers. So what microprocessors have is, so here we have general purpose microprocessors versus microcontrollers. Microprocessors do not have RAM, ROM, input-output ports on chip itself. It is just a single chip which is attached to our motherboard, and then our motherboard has all the buses and all the connections to ROM, RAM, and our input-output ports, which then are connected to our processor. Examples of microprocessors are Pentium series of Intel, PowerPC of Motorola, and Spark of Sun. Applications are desktops, laptops, workstations, servers. Then we have microcontrollers here. These are microprocessors which include RAM, ROM, timers, input outputs on a single chip. So these are very small, but these aren't very powerful compared to microprocessors. But they have all the peripherals and modules on them. Examples of these are 8051 of Intel, 668HC08 of Motorola, AVR of Atmel, Z8 of Zlog, PIC of Microchip, and ARM Advanced RISC machine. Applications of these are remote controls, video games, robots. Microcontrollers are used in everyday applications. Our ACs have microcontrollers, our fridges have microcontrollers. These smart devices that are present in our home, all of them have microcontrollers in them. So here we can see a visual difference of microcontrollers and microprocessors. Our general purpose microprocessors are connected to RAM, ROM, timers, serial COM ports, and input-output ports using these databases. And our microcontrollers have all of them on that single chip. So it does not need such a big setup for all of them to be connected together. Uh, then we have our 8-bit microcontrollers. These are some of the commonly used ones. We have our Atmel one, Microchip, Intel, Philips, Zlog, Dallas Semi, and Freescale Semi. So these are the links you can visit to check out these microcontrollers here, and these are the architectures that they are designed on. The Atmel one uses AVR and 8051. Microchip uses PIC 16 and 18. Intel uses 8051. Philips uses 8051. Zlog uses Z8 and Z80. Dallas Semi uses 8051. Freescale Semi uses 68 HC11 and HCS08. So this is the comparison of 8051, PIC 18, and AVR family. They have programmable RAMs on there. They have data RAMs, which is of maximum size. They have EPROMs, timers, and input-output pins on here. 8052 family, sorry, this has to be 8051, I think so. It has 8K ROM, which is programmable. Its data RAM is 256 bytes. Its EPROM is 0. Timers, there are 3 timers on it. And input output pins, it has 32 input output pins. PIC 18, this package family has 32K of programmable ROM, 2K of data RAM, and 256 bytes of EPROM, and it has 4 timers on it, and input output pins, it has 35 input output pins. XMega 32 has 32K programmable ROM, 2K data RAM, 1K double EPROM. Timers, it has 4 timers on it, and it has 32 input output pins. And these are some of the architectures. ARM, Motorola 68K, PowerPC, PIC 32 are 32-bit microchips. So embedded systems, an embedded system is a controlled system by its own internal microprocessor or microcontroller, as opposed to an external controller. We can see some of the embedded systems in our daily lives. It can be present in our microwaves, our fridges, our ACs, our routers, etc. A PC is connected to various embedded products such as keyboard, printer, modem, disk, controller, sound card, CD-ROM driver, a mouse, and so on. So all of these devices include embedded products. We cannot change these products. We cannot change the chips on our keyboards, on our printers. Of course, if they are damaged, we just simply give them to professionals which can desolder and put new chips on them to make them work. A printer gets data and prints it. A mouse takes coordinates and sends it to the PC. So this is how these embedded systems work. So these are some of the embedded products that we use in our daily lives. In computing, we have our PCs, our notebooks. These are the notebook PCs or notebook laptops that we can call them. Laptops, storage, color printer, laser printer, modem, cable modem, copier, scanner, digital camera. In our cars, we have some embedded products as well, which includes anti-lock brakes, airbags, engine control, transmission control, climate control, collision avoidance, navigation, trip computer, instrumentation, keyless entry. A lot of these are included in electric cars mainly because it is a whole system present in there. In communication, we use wireline phone, cellular phones, PDAs, pagers, fax machines, and intercom. And in cards, we have our banking cards, which have chips in them, electronic purse, social security tools. These are some of the more embedded products. You can read them. So choosing a microcontroller, how can we choose a microcontroller? So we have to look for speed in a microcontroller. Of course, we want speed. What is the highest speed a microcontroller supports? As much speed a microcontroller will have, the faster it is going to process our data, the faster it's going to give us outputs. Then we have to choose our packages. There are dual inline package or a QFP, quad flat package, or some other types. We have our SMD, etc. Then we have to see our power consumption. Of course, battery is a very critical part of our chips. Let's say there are pacers which are put into human bodies. Of course, if our microcontroller there isn't efficient and it consumes a lot of power, then the person is going to need a lot of surgeries to get the batteries replaced. But we thankfully have very efficient microcontrollers which last on a small battery for years. The amount of RAM and ROM on chip, so of course this is very important for the processing, how much RAM and ROM is present on the chip. The number of timers and input output chips or input output pins on chip. Of course, we need the timers and input output pins on our chip to in order to communicate with it. Cost per unit, how much it costs. Of course, this is one of the very important parts as well. uh, when we are talking about large scale manufacturization, cost isn't very high, but when we are making the product in small amount, the cost can go up very high. So availability of compiler, simulator, and debugger is very important as well. So we can test our systems before physically making them and then finding out that it has a lot of bugs and problems with it. And then we also have to look for the availability in the market, because of course, if we cannot find a good microcontroller in the market, uh, there is a huge market gap in there, and it causes a lot of problems. Then we have the AVR microcontroller family. This is the type of microcontroller which we are going to focus mainly on in our course. So the basic architecture of AVR was designed by two students of Norwegian Institute of Technology, NTH, Alf Egil Bogen and Vigard Wallen. were their names, and then was bought by and developed by Atmel in 1996. The AVR stands for Advanced Virtual RISC, or ALF, and Vigard RISC. The AVR is an 8-bit RISC single chip microcontroller with Harvard architecture. We already talked about Harvard architecture, and RISC is a type of architecture which a lot of computers are designed on. So here we talk about RISC and CISC. Uh, in CISC, so here we talk about RISC and CISC. CISC is complex instruction set computer. A large number of instructions, typically from 100 to 250 instructions, are present here. Some instructions that perform specialized tasks and are used infrequently. A large variety of addressing modes, typically from 5 to 20 different modes. Variable length instruction formats. RISC reduced instruction set computer. This has very few instructions here to work. It has relatively few addressing modes, fixed length, easily decoded instruction format. So RISC is generally better than CISC, and a lot of modern day computers are made on RISC because it is not very complex, and it is simpler to work. It is simpler to work on. Then we have our Harvard and von Neumann architecture. Von Neumann Princeton architecture, the same bus is used for accessing both the code and data, as we showed in the diagram. Pentium processor is based on von Neumann architecture. And then we have our Harvard architecture. Separate buses are used for accessing the code and data memory, so both can be accessed at the same time and written at the same time, so it works parallelly, and we can get the most of it. That means that when we need four set of buses, a set of data buses for carrying data into and out of the CPU, a set of address buses for accessing the data, a set of data buses for carrying code into the CPU, and an address bus for accessing the code. So we have all these buses available at all times, and we can parallelly use them. This is easy to implement inside an IC chip such as a microcontroller, where both ROM code and data RAM are internal on chip at distances are on the micron and millimeter scale. So it is good to be present on a microcontroller, because these are very small scale devices, and it is easy to access data and write on RAM on memory. So this is again the diagrams for Harvard architecture and von Neumann architecture. This is the AVR family. The Mega 32 chip belongs here. We have our program flash ROM. We have our CPU, our oscillator, which is simply the clock of the CPU. We have our RAM, EEPROM, timers, interrupt units, ports, and other peripherals connected to it. And the ports have all the input output pins here. Uh, we have four types of port here: A, B, C, and D. And these all have then eight set of pins in them, which can be used for different purposes. Uh, this is the XMega 32 block diagram. Here it looks very complex, of course, but it is not that complex when you understand it. It simply has ports here. Of course, we have four ports here. It has internal oscillators. It has its memory here. Its instruction registers, SRAMs, and oscillators and mux to convert data and to select data here. And then we have the AVR family. The AVR family can be classified into four groups: 32-bit, XMega, Mega, and Tiny AVR MCU. 32-bit AVR at 32, these are the world's most efficient 32-bit MCU. Memory program 16K to 512K bytes, package 48 to 144 pins, operating frequency up to 66 megahertz. These are very fast performance, 1.5 MIPS per megahertz. So then we have our XMega AVR. This is ATmega. The Atmel AVR XMega A series is the most performance-oriented series within its family. The program memory is 16K to 384K bytes. Package is from 32 to 100 pins. Operating frequency is up to 32 megahertz. So not the best frequency, but the best performance out there. Uh, then we have our Mega AVR at Mega chip. These are powerful microcontrollers with more than 120 instructions and lots of different peripheral capabilities, which can be used in different designs. Some of their characteristics are as follows. The memory program is from 4K to 256K bytes. Packages from 28 to 100 pins. Operating frequencies up to 20 megahertz, and performance is from 1 MIPS megahertz. Tiny AVR, this group have less instructions and a smaller package in comparison to Mega family. You can design systems with low cost and power consumptions using the tiny AVRs. Some of their characteristics are as follows. Program memory 0.5K to 8K bytes. Package from 6K to 30 from 6 to 32 pins. Operating frequency up to 20 megahertz, and performance is the same. So these are some of the chips here. We can see all the characteristics here, and these are again some of the chips of the tiny family here. uh, we can see all the data here and what the names mean. So this was the end of it. Thank you so much for watching the video. Share it. Thank you so much.